Okay, today it will be, as said before, no more today the exam, since we finished to present all the argument, the topic yesterday. So we'll do what was supposed to do before the exam, at least one class of review, and to show briefly the whole stellar structure. So here, yeah, there is for the one that are, I discover someone not student that sometimes look at the video. The course is from Chilean university, so was at the beginning Spanish, then they asked to do it in English. So then the notes change from Spanish to English. So it was also easier to me. This is the reason why it's written in Spanish. The strange color is just problem with the scanning because the paper was not white and change it in this light pink. We have seen now everything about about the stellar structure, all the equation, all the characteristics that you need to start to study all the single pieces of the puzzle to arrive at the end, that is to try and understand how is working a star. But also then this will be used later in the evolution part to understand the evolution of a star during its life, starting from the formation of the star to the end of the star. There are several also quite interesting, because there are some and are quite tricky and peculiar. It's really well schematic actually, because it starts essentially terminate as a white dwarf or a collapse. It probably is supernova, but each of the two have different kind that depend on the mass of the star and what is the evolution. We start beginning with the mechanic equilibrium, that is simply classical, the mass by acceleration to a part of mass that is equal to the sum of the force. That has to be zero if you wanted to have an equilibrium. The only main force we have in the star is just a gravitational force, or to be more correct, the force connected with the gravitational effect, because actually the gravitational force doesn't exist, and the pressure force, the force due to the pressure. From the equation of motion, we got that the acceleration is equal, since we have in symmetrical symmetry, essentially all the movement at the radial. So we don't have the component with the angle, so we can take away the vector and just see solving the module acceleration. is equal to force of gravitational effect and the pressure effect. Pay attention, this is minus minus, but not this sum is not negative, can be zero positive. This is because the pressure is higher in the center and lower on the surface. This is usually zero. So this gradient is negative, so this part is positive. This is negative, is positive, you can have zero. Or you can have negative, or you can have positive because if you are no equilibrium. From hydrostatic equilibrium, we got the two expression in Eulerian, the above. The Eulerian and the Lagrangian notation. The each term here is written in negative, and as the radius and the mass increase, the pressure decreases. Applying the integral to the hydrostatic equilibrium, we got the virial theorem. Nice calculation, where we got that potential energy, gravitational energy is equal to -3 the integral in all the mass of pressure divided density on the mass. That is minus or zero. Obviously, this is positive, constant positive, in the minus, in the negative. They have to be because usually the gravitational potential is defined as negative, especially in this case, where you have the potential 0 to infinite and the minus far away, and minus infinite in the set. P divided rho for the ideal gas, you have this equation that can be written in the heat coefficient. This is the adiabatic coefficient and can be rewritten in this way. So relation among the P, pressure divided by density, and internal energy, as is connected to the temperature. So in the end, we have a relation among the real theorem is a relation among the gravitational potential energy and internal energy. Can depend on the state, equation state of the gas we are considering, can vary. Or this is the coefficient adiabatic when it's positively evaporated, or just this parameter here. And we have a classical, we have ideal gas non-relativistic, so kinetic energy of a particle of the gas, there are microscopic movement, that's what we call the internal energy. This can be written as a proportional P by V divided by 2. Gamma adiabatic coefficient in the third, and this parameter is 2. So we have that the U internal energy is minus half of the potential energy. This goes that the total energy, the sum of the two, should be also the macroscopic kinetic energy, but usually really small in respect of the two, so is negligible. We have the total energy is 1/2 of the potential energy. That is less than 0. That is good because we want the star to be gravitational bounded, stay a sphere, not to disperse itself easily. In the case of real gas, but relativistic real gas, we change the gamma is third. this new one, and we have this relation, and where the thermal energy is the opposite of potential energy. So the total energy is zero, so it's not rotationally bounded. It's not unbounded, but it's not even bounded. That, as we saw, can be a source of instability. Relativistic gas can be also a gas on photons. In this case, gamma is infinite, but theta here is the theta here is the one. So it's not always the coefficient element can be defined, but it's permitted. Then the simple equation for the consideration for we cannot have a complete local thermodynamic equilibrium, but we can have a local. That means that we have a thermic and mechanic equilibrium in the gas. Obviously, it can be completely thermic because you have a gradient of temperature, but the gradient is really, really, really small, so we can 1 degrees every kilometer, something like that. So, no, 10. For example, for the sun, you go from, you calculate is like 40 million degrees, the difference, more or less, in the range of 700,000 kilometers. That means divided by 140 divided by 720 Kelvin by kilometer. It's not a big, huge gradient for a star. So locally can be considered quite constant. Then we have to consider that several mean free path of a particle must be less than a typical dimension, and free mean time among collision, it's smaller than the time for macroscopic variation that usually can be calculated as dividing the change in that parameter divided is the temporal derivative. So, for example, the change in temperature divided the time in which the temperature can vary. Changing. From thermic equilibrium, we have the classical, the flux of energy calculated on the surface of the stars. They must be equal to the energy produced inside the star. Can lead to the divergence of the flux is equal to density by the energy production rate by the unit of mass. The luminosity is the area multiplied by the flux. So the derivative of the luminosity see, this one, because you put it inside. You leave to the energy conservation principle. First, like thermodynamics, okay, the change in the internal energy is equal to the change in the absorbed heat, and the work done by the system. That on this system in given so this relation in small amount that leads here to this equation derived in the time that leaves the variation, the time variation of the total energy must be equal to the integrate of the energy production rate by unit mass per unit mass. So it's integral in all the volume on the mass minus the luminosity. That makes sense because if you have more energy produced than it was go outside the stars, this means that the internal energy the energy of the star have to increase in the system in the gas. And we got everything, and then the situation that we see that if the energy of the stars decrease, it means cause decrease means more negative. It means the internal energy will increase, so the temperature and the potential energy goes more negative and the radius decrease. So there is a contraction. You have a contraction, the temperature increase. You have contraction means that the star contracts itself, not that something is contracting. Usually in a gas, the gas to contract itself, you need to lose temperature, have a lower temperature. Here instead is the opposite. If the stars increase its temperature, will contract. And the opposite, if the energy increase, no, let's say initially the energy is negative, so more towards zero, then internal energy drop, the temperature drop, and the radius increase, so there is an expansion. The chemical composition, evolution, just briefly, here is what we talk about, difference with the baryons that are formed by 3 quarks, protons, neutrons, the nucleons forming the nuclei. Leptons are the part that is lighter, like electrons and neutrinos. This we'll see after in the nuclear reaction. Just remember the mass of the neutron a little more than the mass of the proton, and they are more or less 2,000 times the mass of the electron. The electron is really small. The mass of the neutrinos is ridiculously small, because it's like 1/1,000,000th of the electron. And this part, okay, this can be easily skipped because we see later again nuclear reaction. Nice discussion, but it's not so important. Just a relation. It's a limitation of the round trip is going and going back, the reaction, direct inverse reaction. To the balance to study what is the numerical density of a particle. But anyway, we can at the end steam. This is the mass fraction of a certain element, certain particle, essentially how much of the mass, the total mass, is composed by this element. In the case of hydrogen, for example, in the sun, it's like 70%. This can be a function of density, temperature, and the overall composition. This is the variation in the time that depends on several factors, mainly to the nuclear reaction. One interesting part is the mechanical statistics, because a lot of the parts that they are connected depend on that. And it's saying to have a thermodynamic equilibrium, you need classically an adiabatic cavity that are not losing heat or mass, well mechanically isolated, thermically insulated, and in the mechanical, thermical, chemical equilibrium. So the gradient of temperature must be 0, definitely. And this is not perfectly true, but we can see that the equilibrium time scale usually the mechanical time scale is definitely smaller than the chemical one, and smaller than the thermical. The chemical take times, a lot of time, so you can also consider there's not a lot of movement of energy by thermic. As I said before, in stars, the gradient, typical gradient, can be like 10 to the minus 2 Kelvin meter. You need 100 meters to change 1 Kelvin. And the mean free path of the photon is like length of a centimeter. So a photon is essentially constant to the temperature. Then also the length of Debye length, that is the size where in a plasma the charged particles see the others, not more as the electron see the other electron, interact with the other electron, but act with the gas of the electron. Is a system, no more in a single particle interaction. Is 10 to the minus 11 meter. That is more or less the size of an atom radius. So that also can be seen, not the particle interacting with essentially each other, but the plasma, which is a single spike. So we can consider gas of not interactive. There is no collision. It is not different with no collision, but the particle just interact with the collision when there is a collision. In the middle, they just are going, seeing the system, not the single particle. So the interaction are just when there is a collision that leads to the thermalization. We now see the several distribution quickly, and considering these things, for example, the number of in each state divided the total number, the function, the partition function. Each Different distribution have different probability. Here, starting with the Maxwell-Boltzmann, this is all the theory about how to construct the probability for each distribution that we need to calculate. We maximize the probability using also the Lagrange multiplicators, calling one eta beta. It's going inside, and we got this. At the beginning, this is the formula, generic, for the Maxwell-Boltzmann distribution, with the side that is the partition function that are give the characteristic, statistical characteristic properties of the system. This is nice. Then you see that beta, that is the Lagrange multiplicator we use for the condition connected with the total energy. And we see that at the end, the mean energy is connected by beta. That is here the minus the derivative of the logarithm of Z, the partition function by the beta. So at the end, we can see that we can redefine beta as 1 divided Boltzmann constant multiplied by the temperature. That is essentially the typical thermic energy of a particle. If you want to calculate a mean value for some properties, you just sum everything over the properties inside the distribution. It is the weight for each state. Then there is all the calculation where we arrive at the several value. Where you can see here that, for example, if your temperature goes to 0, in state there are energy, high energy are almost 0, down with an exponential. We can, using this statistic, to calculate the classical equation state of the ideal gas, since the ideal gas is following Maxwell-Boltzmann distribution. Then there is a Fermi-Dirac, that is a distribution that follows the exclusion principle of Pauli. They said that you cannot have Maxwell-Boltzmann. You say that you can put all the particles you want essentially inside in the state. The Fermi-Dirac say no. You cannot have a limit of the number that generated by the G I, and then but then taking this number multiplied by 2, we spin up or down. Why in Maxwell-Boltzmann GI is just a weight, probability weight for this state. This is connected with the energy of the state. In Fermi-Dirac is definitely a limit. You cannot fill it more than this value, twice this value. We got similar, the condition, integration Lagrange, we got the classical equation from Fermi-Dirac distribution. where the eta here, before we managed to take away and define with the partition function. Here we define essentially with beta epsilon f that the Fermi energy, the characteristic of the system. Characteristic of this distribution is that we go with the temperature to really zero, so we go with the really low temperature at absolute zero. The shape of the distribution is a rectangular. We have for energy above Fermi energy, you see here, this is higher of the Fermi energy, this is positive. So if this goes to infinity, this is really big, but higher than this, so this goes to zero. So we have no particle above. For equal, this is goes to zero, so this is G this is 0, so epsilon to 0, 1, 1 plus 1, 2, Gi, and epsilon is less, you have exactly Gi. For this reason, usually we consider not as on simply n, but n divided by G, the fraction of this field, the several level. That means that here is 1, here 0, and 1 and 1 half. We can calculate here in general, then observation of the number Lie. This is observation of the particle, of the energy, and if you consider the T that is smaller than 0, that is an easier way to calculate, we can get that this typical energy is just proportional to the numerical density of the particle. And so the total energy of the gas is even connected with the Fermi energy and the numerical density. Here you can see more or less a value can be 0.27. The mass here we are just putting m is the mass of the particle and not put electrons, but just the typical. And this energy is proportional to the inverse of the mass of the object. If you consider this is in unit of electron mass, and depend on the density. Here the density is in unit of 1 million grams by cubic centimeter. This is in mega electron volt. It is not small, considering that an electron has a rest mass of half mega electron volt. And you see if you have, for example, if you are considering electrons with exactly this density, because usually when a gas starts to have effect of degeneracy effect, the degeneracy effect are considering when we'll see the effect of this one, that the state start to be filled, and you start to see this characteristic of the Fermi-Dirac distribution. So it start to behave like imposed by this distribution. And for electrons. This means that an energy Fermi is like a chemical energy about 2-3 billion Kelvin, so really high. You need a really it's a really high energy. And also, if you see that you are here putting a proton, that this everything starts to go down 2,000 times. That means that are just going to around 1 million. So it's typically in the stars have more than 10 million. That means usually the protons are well an energy well higher than Fermi energy, so the degenerate effects are negligible. Then there is Bose-Einstein, that is there is no Pauling, particularly Fermi-Dirac are for fermions, particle with autofunction symmetric antisymmetric autofunction. Should here, yeah, antisymmetric autofunction with semi-alpha spin. 1 alpha, 3 alpha, and so on, plus minus. Why Bose-Einstein? Recently we talked about the Bose-Einstein matter that was formed finally are with the integer spin. Usually this called boson can be photons or phonons and other times, but every essentially particle have an integer spin. That means also an alpha particle, that is the nucleus of helium, that since have 2 protons and 2 helium, 2 protons and 2 neutrons. Since there are 4, you on the composition always you can have alpha spin, but globally the particle is in integer spin, so correspond to the Bose-Einstein. In fact, one way to have this Bose-Einstein compound is with the nuclei of helium with a low temperature. It's similar, it's just that you can have all the particles you want in every state. And usually we take away the limitation of conservation of number. Photons can be observed or reproduced, it's just energy you conserve in the photons, not the number. So you take away, you get this equation that is similar to the previous, but here is a minus, not a plus. With some change calculation, we go back to the energy, the Planck equation. Little resume that for all the 3, it can be more or less expressed in this way. G is the number how the weight of the state according to the energy of the state, with this above connected with the energy modificator for the energy conservation of the particle. It's exponential of this one plus the sum that is 0 for the Maxwell boson, plus 1 for Fermi-Dirac, and minus 1 Bose-Einstein. Usually we use the n divided by g, that is the occupation index or spinning factor. The eta is what is called the parameter of degeneracy. Usually for Maxwell-Boltzmann, it's really high. And when this is really high, we have an ideal gas regime with no degeneracy. when this is more or less 0, we go toward the Bose-Einstein. You have start to see some effect. While when this is definitely less than 0, remember in Fermi-Dirac we change decently with minus beta epsilon f, the energy of Fermi energy multiplied by beta, minus, negative. This start to be a strong degeneracy that means really high density. Actually, just if you have strong degeneracy, you can have low temperature or higher low temperature respect to energy, Fermi energy, or high density. But also, it's if you want complete degeneracy, you can only go to the absolute zero. No way. And there is another way. Here it's the some, as I said, if n is greater than 0, then you have this solution. If n is definitely less than 0, you have here. You can simplify. This is in general. This is greater than 0. This is just this is take away anyway. You see here. If you this is really big, doesn't matter how much is what is this. This is negligible, so you take away and go directly. So approximate the maximum Boltzmann. Every single distribution, if the eta is still it's really big, is go with approximation maximum Boltzmann. If really negative, it's you see the effect, and you see that I have this shape of rectangular shape that is classical for Fermi-Dirac. In Fermi-Dirac, n divided by g must be minus 1. G have his probability plus the 2 for the spin already included. And here you have characteristic. Maxwell-Boltzmann is an exponential. Fermi-Dirac have when this, you can notice you have this shape. In Bose-Einstein, and the characteristic can be really big in near the 0. They have no way to pack themselves the photon at the same state. From here, you can go with the layer Boltzmann law. Then you can compare two states, and so you have the ratio, the number of particles in one state and in another is equal to the ratio of their weight multiply the minus beta by the difference in energy of the two states. Then just remember that statistical distribution is the number of particles inside of the state, with G the number of state for each value of energy. It is the density factor, and the fraction of occupation multiply. And usually you can calculate in this way or this way. This is according to the momentum or according to the energy. Here the G total GD is the value for the degeneracy. In Fermi-Dirac, this is 2, for example. In other case, you can have also 2 for the polarization of the kind of in the case of second photon. Okay. Let's show you these things. This is the behavior of the several free characteristic distribution according when we start to decrease the temperature, for example. So going to compact to the lower, feeling the lowest state of energy. You see the Maxwell-Boltzmann just going down with as an exponential normally. The Bose-Einstein is going to fill essentially almost all to the lowest, with the really peak at the basic level, zero energy. Fermi-Dirac have instead the opposite, while the other are going, the collapsing toward the vertical axis. The Fermi-Dirac for the degeneracy, since you cannot have more than two particles for each state, that means state in the space of phase space, means position and velocity, the momentum. So when all the other characteristics are given, you can have just two particles for these properties, energy properties. Remember, for example, in the in an atom, you can have several orbitals, and but each orbital is defined by the quantum number of energy, the n, that is the line in the row in the periodic table. Then there is the shape, they are more or less in the vertical group actually, and then usually, for example, hydrogen and helium have just one level. One, it is the spherical one. So you have one defined by the energetic number and the momentum number, and then you have the two possibility for the spin. Lower on the second part, you have the lithium, beryllium, boron, nitrogen, carbon, oxygen, low in neon, that you have the two level, because you have the spherical one and the momentum 1, spherical momentum 0, the other 1, and for each of these two you have two different, and that brings you have 8 possible electrons. Essentially you have 4 orbitals, and for each orbitals you have 2. The 4 is the G, essentially in general, plus multiplied by 2, because you have a degeneracy, so you have 2 addition. The characteristic you can see, generally, when you're really high energy in the system, you don't see a lot of degeneracy. Fermi-Dirac, Maxwell-Boltzmann, Bose-Einstein are quite similar, except that Bose-Einstein are really higher in the central part. Maxwell-Boltzmann a little less, and Fermi-Dirac, as I say, doesn't like to be in the same energy state, so probably is the least, and try to feel more here. When you we start to have, usually here it's when this energy is relatively higher than the Fermi energy. So you don't see the degenerate effect in here. Then you start, you see here. Mu essentially is the Fermi energy. When the energy of thermic energy is comparable, you see this shape, when since linear exponential, it is similar here, so similar to behavior, similar to the Maxwell bonds. As more is small respect to the Fermi, the internal energy of the thermical, so you start to notice the effect. You have more this box distribution. Here it's already with the alpha and the internal thermical energy alpha or the Fermi energy. You start to notice more. 1/10 definitely is noticeable. 100 is definitely. This is not still complete degeneracy, but you can see because you prevent complete degeneracy, you have to go to T0. That is completely square. But you see, already in this here, degeneracy a really big effect with a nice result. So this. And here is the limit imposed by Pauli's principle. The Fermi is here, the line is the limit imposed by Pauli's principle, and a lower temperature you can the Maxwell Boltzmann is definitely different, but at higher temperature, the Maxwell Boltzmann can follow this limit, so the Fermi Dirac can be similar to the behavior to the Fermi Dirac, to the Maxwell Boltzmann. We talk about thermodynamic equilibrium. When you have this equilibrium, we can manage the radiation with the Planck law, the gas with the Boltzmann law, in gas radiation with the Kirchhoff law. Maxwell, Boltzmann, Einstein, here statistic, and Maxwell Boltzmann statistic. These things can be define the equation state. Usually with the pattern equation state, you see at the beginning was defined as a number of moles divided by volume. P per D equal N, the number of moles, the R, the real gas constant temperature. But this is more in chemistry. In physics, you prefer to change a little. And the number of moles is just the N divided the number of Avogadro number. But N divided by volume is the numerical density. And if you multiply above and below by mu, that is the molecular mass, the mean mass for each particle, and in unit, atomic unit, mH is the atomic unit mass. The mH because it's more or less the mass of an atom of hydrogen. Not exactly, because by definition is 1/12 of the carbon atom, the atomic unit mass. So you multiply here and here, and the numerical density by the mean mass for each particle is the total density. And mH multiplied by the Avogadro number is by definition 1 grams. So you have this value. You can substitute. Okay, we demonstrated that the interaction of the particle are in Coulombian interaction are negligible. We have a complete ionization of almost. And here it was the calculation that Coulombian energy divided by internal energy of the gas is this value that we calculated and so on. Usually, it's, you see here for the sun, the Colombian energy is 101% on the internal energy, so it's negligible. You can neglect the consideration of Colombian interaction. Then we have all the description to calculate the pressure in general. According as usual, the pressure is just to see the variation of momentum. Pressure is the force by the surface, and force is the variation of the momentum with time. Divided by S is the flux of the momentum. So we know all the consideration and not review this part. But we got a general equation that the pressure of a gas is equal to this value. 1/3 the momentum of the particle by the velocity of the particle. You cannot, usually classically, the momentum is the mass multiplied by the velocity. But you cannot change it because this relation is just valid when it is not relativistic. When relativistic, it changes. And the number of particles with a certain momentum are given by the statistical distribution we saw before. And when you consider a non-relativistic gas, we have this value. When you have a relativistic gas, we have this other value. Where we got the, for example, the pressure by radiation is 1/3 A, it's a constant, this value. Sigma is the famous Stefan Boltzmann constant. See the velocity of the light in the vacuum. Here, to the relation we saw before, is lead the theorem variant that is not necessarily bound, and this behavior that goes up and down. But if you contract a star, it will increase the temperature, it will expand decrease temperature. And we defined that in general we have pressure of ions, electrons, radiation, so pressure of the gas and pressure of radiation. The pressure of the gas divided by the pressure is what is beta. It's not the beta on mechanical statistic, but another beta that is among just from 0 and 1. They are giving how is important the pressure of the gas respect to the total pressure. When beta is 1, we have the gas giving all the pressure. When beta is 0, it means that is the radiation there, giving most of the, almost all the pressure. The molecular mass we mentioned before. Here is this is quite important because it can permit to put all the chemistry here. And how? In this way, you see, the mole can be defined as the inverse of the sum of the fraction, mass fraction for the element divided is mass number. Then in practice, considering the ionization, if you complete ionization, we can have the relation for the molecular mass of the electrons, and molecular mass for the ions, with the total, which is the sum. This is a typical value for the sun, and they depend on X, that is the fraction mass of the hydrogen. Y is the mass fraction of the helium, and Z for the metal, that in astronomy every other element are not hydrogen and helium. You can see here that the pressure of the helium, this are the pressure of the electron are generally a little bigger than the pressure of the ions. Electrons are really smaller, but are definitely more, because, for example, in hydrogen just release 1 electron, but helium release 2. So you have the double. Just a little break now to okay. And again, about the generated gas, it is important to understand why we have the generated gas in the star, because obviously temperatures are not going down. Usually the generated gas in the star are of the order of several tens of millions of Kelvin. So what happened? You have to consider the generation is given by two principles. One is the exclusion principle of Pauli. You said that you cannot have two particles, two fermions with the same exactly same quantic number. So you have a difference in spin. The reason you have usually two, one up, one down. And the other is the certainty principle that start to be strong. A certainty principle saying that if you have two conjugate variables, their precision, their error, the uncertainties for each the product of the two must be equal or greater than a certain value. That is, in this case, we have the volume. The volume from the momentum is greater to the constant of Planck to the cube. That means, for example, if you're just considering one direction in monodimensional space, so we have just moving along a line with certain temperature. We have the two, what is going to what is called the phase space, that consider position and momentum. In this case, is a space. position and its velocity, and we are packing there. If you have several particles, it's said that if you usually are scattered around in the space, you obviously you cannot have two particles in the same position. So you put in position far away, but in consider with the same velocity and same energy, you just can have two in different positions, but two. If the energy of the system is quite high, they can distribute really well everywhere, and there's no problem. But if you start to increase the density, that means we are packing everything. It means that the space that each particle have for itself start to shrink. So accordingly, the space that the variation of the momentum possible is connected by this variation. So it increases. To give and what happens usually if you have a low density, this delta momentum doesn't mean a lot because it's really small. H is 10 to the minus 26, if I remember, something like that. So it's really small, doesn't matter. But if you start, so it's meaningless for the typical value for the momentum. If you start to pack really well, all they start to increase, and suddenly this uncertainty momentum start to be comparable with the mean momentum of the particle. That means that the particle start to have this momentum is start to be more influenced by this uncertainty, and start the mean momentum of the particle start to lose connection with the temperature as it should be, but more connected with the limit given by the uncertainty principle. Up to a certain point, when are really high density, so you are really packed, you find that the particles with the lowest energy are really well filled. You cannot put another. So the particle you are filling that box, as we saw before, increasing when the Fermi energy increase that is connected with the density, and you start to have the shape, and when the shape is not more like similar to an exponential, but start to be similar to a box. The box. The temperature is not, the role of the temperature is not so strong in the meaning value for the velocity of the particle. That means in this way that the pressure of the gas to be disvinculated, no more connected with the temperature. It is a reason why not just with the, if you drop the temperature, it's easy going, every particle will go to the lowest state of energy. So you think that the box in this case is because you start to sense the uncertainty principle, and this delta P started to increase and be comparable with the mean momentum of the particle. You have this equation here, it's going over the with the total degeneracy, data say definitely smaller than 0, high really negative. You have this box shape, 1 in the center and 0, and you have this solution that is the number is just 2 divided with the volume, can be rewritten as saw before by the certainty principle 2 divided by the volume in the momentum space volume divided the unit of the phase space, a cubic time constant can be written this way. You recalculate, then so you calculate the mean momentum characteristic. This can be written this way. Here in mass of the electron. If not relativistic, you have this situation. You can see here that the gas, the pressure of the danger gas is to the inverse of the mass. So the electron is definitely higher definitely pressure than the positron. Neutrons, not so much, because usually neutrons are stable only inside the nucleus. Outside, they decay quickly. And the molecular mass is the composition. In your case, it is not relativistic. Relativistic, we have the two situations with the pressure that depend only on the density, changing the exponent. Usually for relativistic, you need like more than the order of 10 million grams per centimeter cubic. Water is 1 gram per cubic centimeter. So you have density here, we are talking about density 1 million times of the water. Here you can see it's when it's not in the range for relativistic in this way. When it starts to be relativistic, there is this deviation from, as I saw before, from similar to Maxwell-Boltzmann, and you start to see the effect of the degeneracy. If you are usually the degeneracy, it can be partial, not total. In this case, you see here that can be written in two ways. This is the general equation for the partial degeneracy. Approximation you can see as a classical ideal gas with a contribution, additional contribution by the numerical density reduction. Here is like reducing the effect of the temperature, or the classical for the density with an addiction on the effect of the temperature. This is what we saw, that essentially when start to change, raising the temperature, the pressure starts to shift from something that is similar to total degeneracy, or a state where it is not ideal gas. It's because usually the equation state is not perfectly one or the other. Here for the pressure of the gas, the calculation, you see again, and the energy, quite simple to remember. How this is working? Essentially, the photons are passing, and with the interaction are leaving a little small of momentum. Also, a photon has a small quantity of momentum. You see, the energy is P per C. Momentum of photon is the energy of the photon divided by C. And this interaction are leaving this quantum momentum, so it's like having a pressure. Because so the gas interact with collision and add little momentum to the surface. Here we talk about the battery exponent where we have the three different battery exponents that when they are equal are the battery exponent as we know. In the meantime, in the genetic gas, these three coefficients can be not equal. When they are equal, each one is just when we have the battery process. And so with the ionization can change, and as we saw after in the coefficient is important for the stability. So since there is a change in the adiabatic coefficient, we have this is of the calculation, and here remember the adiabatic this is quite complicated. The potential energy, potential ionization potential, and the thermal energy of the gas. It can be smaller than fructose, that means they are causing dynamical instability. So after the radiation equally can vary. We have the same coefficient, but one where equal are the adiabatic, equal to the adiabatic one. In this case, when b is at 0, the adiabatic coefficient goes to infinity, so are equal among them, but not equal to the actual adiabatic. Here, definition of the specific heat. We assume that the pressure of the gas is the sum of the two components, and this generically for in a star, this is the pressure. The part given by the radiation and given by the gas. I know that we talk about radiation, how's interacting, talking about okay, here we are back in English. The opacity and the minus opacity density of the thickness of the layer is optical depth. And fun fact, the location of the photosphere in a star is defined when this optical depth is 2/3, looking from outside from our point of view. So when the optical depth look inside reach the 2/3, that is the radius of the star. It changes a little with the radiation, because depending on how that frequency is interacting with the gas. The opacity is defined. I didn't wrote here, no, but when you see the opacity by the density is the opposite of the length, so is inverse. In fact, is the free mean path of the photons. So you see that the opacity is like a surface divided by mass. It's something strange. The interaction with the matter can be Thomson or electron scattering. An photon interacts with an electron, they are scattered away. There is no change in the energy of the photon, just in this direction. And the opacity doesn't depend on the frequency. This is just constant perfectly. At higher temperature, you are going electron scattering become the least inversion, that is the Compton scattering, and there the energy are changing. Or you have a free absorption, and when the photon interact with an electron and with an ion that absorb the recoil, and you have with an electron with ion energy. That is essentially the opposite to the Bremsstrahlung, that the opposite of the electron pass nearby the potential of the ion and emit the photon. Then we have the bond-free interaction, essentially ionization. Usually it's in the inner part just for really heavy element. Usually the gas is completely ionized. So usually BF is just working. These two are working more in the core of the stars, and here working outside in the envelope of the stars. Or also there is the inverse additive combination. Free bound, an electron here is bound, and this free absorb the photon, or the electron combined with an ion and is bound and emit a photon. Bound, photo excitation, arrive at a photon is absorbed by an electron that goes to the higher state of the orbital around. It is needed definitely outer part of the envelope, temperature lower than 3000 Kelvin. Also beta bound emission, spontaneously induced by collision, even lower temperature. Then we have the bound free by hydrogen with an additional electron, so an atom of hydrogen with 2 electrons. Something strange, but this can happen in an outer part of really cold, cool stars like supergiant, red supergiant, red giant. Here explain B is bound, F free refracted to the electron in the process, or interaction with the dust. Also here it's really cool, the molecular star outside. Now we are usually just considering this part, the electroscattering, free absorption. This is mainly in the envelope. And remember, with the Einstein coefficient, the variation on intensity change with the spontaneous emission, induced emission, and absorption. Spontaneous emission is just when an atom emits a photon, because it's excited and emit. Induced emission is that arrives a photon, collide with an electron that is in excited state, and the electron can decay, emitting a photon with the same frequency of emission. That means that the electron in orbital is excited of a certain difference of energy respect to the one level below where you can decay. An electron cannot decay in every level below. It has to be maintain conservation for the momentum, since we are emitting photon, can be anyone. And if this difference of energy arrives a photon with the same exact energy, that this interaction can cause the electron to decay to the lower and emit a photon that is an exact copy of the photon that arrives. That is the principle used for the laser. And then there is absorption. This is called the Einstein coefficient. Einstein also worked with this stuff. Then for the opacity, we have this general formula: opacity for bound free, free, and scatter, electron scatter. These two are mean inside of the core, for example. Bound free more in the envelope. And this takes account for induced emission. We define the Rosseland opacity, defined in this way, that is a mean. To simplify the calculation, and we have the Kramer law for the opacity that is a constant part and dependency on density and temperature. For the electroscattering, we have the formula. You see, usually it's quite small, 0.4. For free, it's definitely bigger, the value. And in the shape of the Kramer law, and actually this is actually what is called the Kramer law, with A it is 1 and B is minus 3 alpha. And bound free can be described in this way, and you see that is 10 to the 25, really high, but just outside. But we say that usually the convection due to high opacity is more in the outer part of the envelope. And again, the mean free path of the photon is 1 centimeter. That is, see that in that range the gradient is definitely small, so we consider temperature almost constant. The problem would if it's a local thermodynamic equilibrium, then we have black body. But if it's isotropic, non-direction will not be a flux, but the gradient is small, but not 0. So you can have it's almost like it's a small deviation from the body, but that deviation is enough for create a flux and radiation. This is here the way to calculate the relation for the radiative luminosity, that we arrive to this value. Is the femoral relation among luminosity, certain radius with certain gradient of temperature, certain opacity and density, or the opposite, the here in Eulerian Lagrangian form, or the opposite, the gradient in the temperature, as there is the the consideration for the convention, just mention that we saw more. There can be a flux for neutrinos, but since the mean free path of neutrino is more or less like 100,000 solar radius, just skip away, it's just subtractive. So when we are considering the nuclear reaction, this loss in energy is just considered inside the epsilon. In the other process is counted as a luminosity loss and energy loss. There is no interaction. In the massive phases, when you have a really high density part, you can have interaction, so you need to consider also this interaction. The conduction, as we saw yesterday, usually it's the mean free path of the electron and ion are really small, so the conductive flux is definitely smaller than the radiative flux. But in degenerate gas, since we have the Fermi energy, that is what is saying how much is the momentum, is definitely higher than the usual kinetic energy. This means that the conductive there is working. But usually we put together relatively conductive in flux, as we saw in this combination. Usually this is really it's quite big, so doesn't change a lot the sum. Then when in degenerate gas, they start to be definitely small, so this is too big and be commanding the equation. Nuclear reaction. Quickly, so usually if you consider the mean value of epsilon on all of the stars, we can see luminosity divided by mass completely. That is 2 erg by grams per second. It is not so amazing, but this is because the mass is really high. So, and also because the real mean, you should consider, okay, total luminosity, but not all the mass, just a fraction of the mass of the core. So this can, once we know this value, actual, we can calculate the mass of the core of this fraction. As we said, we have nuclear particle, bosons, they are spin integer, non-negative, photon, meson, alpha ray, phonons, fermions. They are 1 alpha, and electron, protons, neutrons are mainly interesting. We have particles in the hadrons that are the massive. They are made by quark. The baryons are made by 3 quark. The meson are made by 2 quark. And the lepton, the light. Hadron came from the massive, electron from the light, from the Greek. The leptons are not connected with the strong interaction. Strong interaction are working with quark, so just with the proton and neutron. The ray famous dividing alpha, beta, and gamma. Alpha rays are nuclei of helium. Beta rays are the electron, and gamma rays are photon, usually of energy of around 1 mega electron volt. Type of nuclear reaction, we have the fusion, spallation, where nucleon is hit by a particle with enough energy to break it. It is typical to produce lithium, beryllium, and boron. These are not produced mainly in stars, but usually particular for the spallation or in outer part of the stars. Lithium, for example, just started to have a reaction easily at few millions of Kelvin, so quickly destroyed before it can start to burn hydrogen. We have induced gamma emission. alpha decay, fission, beta decay. We can usually write the relation in this way. We have a main particle, a project particle, target, and then the product, one main and addition. Like we contract the production this way. The target particle collided by the A, that is the projective particle, produce the Y particle, the result, and B usually it's a smaller particle as an addition. Remember, you always need to consider the conservation of angular momentum, speed included, charge, rest mass, mass energy, baryonic number, leptonic number. The number is baryonic number, the number of baryonic and leptonic particles you have. A baryonic particle proton have 1, his antiparticle is -1. So if before you have no leptonic particle, you have leptonic man in the beginning 0, so you have conservation. So it's, for example, a neutron, the decay must have leptonic number at 0. So at the end you have leptonic number 0. Since you are producing a proton and an electron, you need another leptonic particle like a neutrino to have a -1 to take away the 1 from the electron. Usually the nuclear reaction are produced in this way. The two particles react, produce an intermediate excited nucleus, then KDK in several channels. The same particle as before, elastic scatter, then target atom nuclei particle excited in elastic scatter, another with the particle emission, relative capture, actually is emitting, but it's called relative capture, or fission, the particle is excited, intermediate nucleus is breakdown. The channel parameter depend on the energy of this excited nucleus, the angular momentum, the parity, not on the way. If you use the same excited nucleus in several ways, the channels that are going outside are depending just on the here. It's essentially forget how this was produced, just on the situation. Remember, the Q value is the rest mass of the reacting particle less the rest mass of the product. This is mean the energy that goes as free by the nuclear reaction. Can be expressed also in what is called the mass excess in this way. Usually it's negative because m is less than the sum. A is the mass number of the object or number of nucleons inside the nucleus, and MH is more or less is the mass of the nucleons. Actually, just let's say the 12th part of carbon atom with the electron, but simplification you can use this one. The variation is on the then no less 1%, so not so important. The binding energy is nice. That is the energy when it's like see the Q value, because the different in rest mass, but where the reacting are the single nucleus taken singularly, And then as a product, the mass of the nucleus of the element we are considering. The binding energy, in fact, is referred to a particular element. This is for a generic reaction. This is a property of each element, of the nucleus of each element. So, for example, in hydrogen, it's just one proton. So, you have one here, the mass of the proton, here it's 0. And what is the mass of the proton? So it's 0. The binding energy of the hydrogen is 0. 0 because you don't need release, there is no release of energy producing a proton, just a proton. In helium, instead, you have here the two proton. 4 is the atomic, the mass number of the helium. 4 here, that is two neutrons, because you take 2 protons, 2 neutrons, put together, take away the mass of the actual mass of the nucleus of the helium, calculate the rest by C, this difference in rest mass, you have a certain value. It actually is more or less here 7, 8. And Mameli is used the B divided the A, the atomic number. This is because you see there is this shape that is going up to more or less go to the iron, and then goes down. That means if here, if you are fusing to the element, you are producing energy up to the iron, while after ion is the fission of an element. So you take an energy, split in 2 parts, are producing energy. This part here increase due to the surface tension effect. At the beginning, the nucleus are just on the surface, so can repulse better the tank state, easier to pack. But when the number increase, then you have to be nearby each other, so before you can stay a little far away and permitted to put together more. And here is the function, Coulombian repulsion. It is nice to see, in fact, that there is a relation between the Q value divided by atomic mass number and the binding energy divided by mass number in the case of a simple fusion. If you have 2 particles fusing, identical particles fusing to get another one, with the double of Z in A, you see there is a relation. There is essentially the difference among these two. So you consider if it is the product is here and the reacting is there, the release energy by number of nucleus is this difference that gives us exactly that for a fusion of 2 particles it works just here, then it is exothermic, here is start to be endothermic, which are absorbing energy. Here is more or less a value for the binding energy by mass number. And here you can see the part that is for the tension effect, that is in inverse of the radius, that is, so area of volume r to the 1/3 this part. This is the Coulombian, and but since you see here the difference should be in similar the behavior, but actually since A and Z are more or less connected at higher value, this is just going with the A to the 2/3, so have this behavior in this way. The reduction is different here. You see this is a certain value that is reduced a lot here when A is small, and less here. Here should be since A is really big, it should not reduce a lot. So why should decrease? This is a real connection. This is for touch 1.3, this is 2. So at the end is we have that here is increasing with A, this value, so more negative is taking down again. Then we saw the nuclear reaction rate, nice calculation, all the theory to calculate the reaction rate that at the end of this value. So epsilon is the rate here with the density, numerical density of the two particles and the cross section, mean of the location and velocity among the particles by the Q value of the reaction divided by the density. You can see it's, oops. At this value, this is given if delta x depend if it's 1, if the two particles are equal, are the same, and 0 if are not the same. This is because you have considered the two cases. If you are have the same particle reacting itself, obviously you have a less number of possible reactions. This is happening the other. Then you consider classically with the potential energy, you have this problem. The particle should not enter, and the tail of Maxwell distribution is not enough to have something here. But even if you have a particle can enter, to pass, once it's here, it enter but also go outside, because have enough, not too much energy to stay inside, to fuse with another, stay inside. So how is this possible? It should be impossible to have a nuclear reaction. In fact, it was thought at the beginning it was not possible to have a nuclear reaction in the sun for this reason. But quantics say something different. For example, in potential wells, you have a particle are passing above a potential well. Usually, a classical particle just pass over. Okay, enter and go outside and continue. It's not blocked. Instead, in every discontinuity, there is a probability of reflection. So the particle can reflect on this border, going back, or enter the pass through the wells, or enter in the well, stay in the well for a while, then go outside. Also, if you have a wall, we saw for the quantic that the probability of existence of the particle is a function wave decrease exponentially inside after the wall, potential wall. So if you go inside of potential UV that can enter and is probability exists goes down, and there is a small probability that the probability can pass through the well and find itself inside. Then there can react inside up to manage to do the reaction or do the opposite and go it back. In blue is the potential energy. In red here is not the potential, is just the probability to be there. That is what we call the two effect, and then go with the explanation of the energy. Higher the energy is can go higher. And the end, the cross-section can be calculated in this way, where part is a geometric, classical cross-section, just the, like hitting a target, the biggest the target, the easier is to hit it with the particle. In this case, it's little different, but it's still proportional, and then it is not this size, it's not is radius, but was called it's connected with this wave number, the size of the wave function. Several parts. The T is the transmission for the normal, for A normally. The resonance factor, symmetric, the branching radius, the probability for each channel. The transmission is what it takes in account the also the tunnel. At the end, do all the calculation. We got to this situation where we have several terms. Quite complicated for the energy, the Z and the A. They show that is it's quite complicated. Essentially here you can see is a two-term exponential and with the square. We have the famous for the what is called the game of wind. It changes with the higher atomic number is definitely less difficult to have the reaction, obviously. The resonance is just that for certain energy, you have some reactions that can, the particles can stay inside here in the bound part of the nucleus, inside the nucleus a little longer and permit to have a reaction. Usually several reactions that otherwise should be too, not so many reactions, but for the resonance in us in this way. And before, thanks you to the tunnel, you have this what is called the game of window, because of this exponential, it goes down, the other part that goes up, it is stronger the transmission of ion energy, and the multiplication is let's see, show you. It is here the exponential from Maxwell-Boltzmann for the transmission. And you have this product that it is semi-Gaussian shape that permit to have. Usually, we see that usually for typical energy for the nuclear reaction, this range of temperature, energy of the max of the gamma window is exactly where we can have the range where you can have the particle inside. It's more than 100 kiloelectron volt the energy for proton, for a particle in the core of the star. The resonance is just a peak given by this way. So the particle, you have an enhancement of the cross section that goes as this peak. If this position is quite near the gamma window, can increase it quite enough to have more reaction and should be the user. Then there is an electron shielding. It can be that can help to attract, because the attract electron nearby, so two atoms see less each other and more the electron to manage to arrive in more nearby and more reaction. And this one is really strong, is what is called a pycno-nuclear reaction. Pycno is the density, so reaction connected with the density, not with the temperature, that are thermonuclear reaction. Usually, to have a pycno-nuclear reaction for the hydrogen, you need 1 million gram per cubic centimeter. For the helium, 1 billion gram per cubic centimeter. For carbon, 10 billion. Then nuclear reaction, we have this. Quickly, the several type, we have helium burning, proton-proton, we have free channel, proton 1, the classical, proton with the proton, then produce deuterium, deuterium with the proton, helium-3, 2 helium-3, and helium-4. The first one is usually definitely really difficult. You see, usually you have one reaction every 10 billion years. This is because to form the helium-2, that is in the intermediate here, you need the proton must be antiparallel spin, otherwise there is a scatter. Then you have helium-2 is unstable, you need a B plus decay, or there will be a scatter. And then we need another change in spin split inside, because antiparallel spin are not the basic one. So it's otherwise it can be too excessive, it can be split again and form it goes back to a proton neutron that will decay in the proton and an electron and an antineutrino. You have here the energy product by each reaction, and the energy action by nucleons is 6.6 megaelectron volt. To calculate, you have to remember that the first two reactions are needed twice to have then the third. Then you can have enough helium produced or already present. You can have the proton 2 and 3. They are usually more efficient at higher. Usually proton 1 is efficient up to the 10 million. And proton 2 among 13, 23 million degree Kelvin. Above 23 million is proton 3. That is quite more complicated. It's just reacting with several to produce, but not producing this element because it's just an intermediate. In general, you have this value produced 26 for each reaction. The dependence with the temperature is quite high, 36, not so much. A reaction of volume 3 with the P is not observed actually, while a reaction with the 2 proton and electron produce deuterium, it's really small, but okay. If there is presence of carbon or oxygen on nitrogen, you can have a CN start. This usually it's really efficient above 15 million degrees, and this is the main reaction that is used when the stars are mass enough, usually higher than 2 solar mass to produce this reaction. We use the CN cycle, CNO cycle to produce. The main part here, you can see here the times for production. The longest is this reaction. Essentially here the elements are just catalyst for the production of you fuse 4 proton in 1 helium. But this reaction is really slow, so this causes that mainly this is the last one to be reacted. Even 19.9% is this reaction. There could be, if the energy produced is similar to proton-proton, can be also this one, but definitely more difficult to be there. For example, this reaction also is resonant. What is peculiar that the CN-CNO cycle has a really strong dependence on the temperature. That I remember this will help for the convecting. In fact, usually start they are using CN-CNO as main way. Product energy is at convective core. Usually 1.5 to solar mass and F stars. The CNO more productive. You can see here with the temperature, the logarithmic of the production is TP is start like 5 million to be effective, then not grow so much, while CNO can around here start to be RIMA and produce a lot. One something really interesting effect is that they're changing. If you're considering the fraction mass with after the CN cycle respect to the proton-proton normal, you can see that the usually the carbon-12 is depleted, while in nitrogen is definitely enhanced, it's also depleted oxygen. At a burning vacuum composition, in neon sodium cycle, that transform neon in sodium, that is most important because it's the lowest. So you have mainly in shift, the neon is changed in sodium 23. Not really stable, but. And usually working with, you see at 30, 50 million degrees, essentially where is the working the carbon CN-CNO that consume oxygen. So a star that are doing this cycle usually have an enhancement of the sodium and depletion of oxygen. This is what is observed in some cluster when they are the small, less massive stars, they are contaminated their composition by the more massive stars that are already evolved, that they absorb this gas emitted by the more massive stars when they're dying, and they found the sense with the chemistry, with this situation changed, with the less oxygen and more sodium. Why the magnesium aluminum cycle directly change the relation among the two, and you can see this variation evenly as before. The helium burning arrives at a higher temperature. This is because you cannot burn helium directly to produce beryllium, it's unstable. This is because I show you I go here. As before, you see the nucleon binding energy by per number of nucleon is increased. If you see in detail in here the part, the beryllium, it is 9 after declinate is in this part, it's less stable, but in the beryllium 9 have a lower energy. So if you put this together, it's trickier to have produced beryllium. You need to free helium to go directly for the carbon. Oh, no, it's not. No, it's not, was not showing, seems. Now should be easy. Okay. Now I'm showing you what I was talking about. You see that beryllium is lower. This is the problem. Little problem. Or not. I can understand here exactly what is showing. Okay. Here, helium burning. You have to produce this beryllium that is a really short life, 10 to the minus 16 seconds, really short, but is enough to interact with another in the reaction is resonant at the second level and produce. In fact, this was discovered essentially because if there is not this resonant, there will be not so carbon abundance, so also not possible so much so easily life based on carbon. There is not so much carbon in the universe. Just here to have an idea, the time for the lithium 5 can be formed. It's producing with the helium with the proton is even less, 10 to the minus 22 seconds, really unstable. but lithium needs to be lithium-6. The production, you can see the production energy is not so much. If you're going to see per number of nucleons, the nucleus is 0.6, it is 1/10. That means so the time of the life of the stars during the helium burning is usually 1/10 of the pass during the hydrogen burning. And you can see here the behavior of the production with the temperature is really high, independent. So it's also what I remember is helped to have a small, thin shell in the burning that will bring the stability. Then you can produce some burning helium also with carbon of oxygen, neon, the neon magnesium, with less production of energy, you see, less. And if you have enough natural CNO production, you can have this other that produce many neutrons with this useful for other. The burning will be higher. Helium burning happen on 100 million degrees. We are 6, 7. And you see, we are found like 1,000 years away from the core collapse. When start the carbon burning, the star will collapse at the end. No other way. And we have this possible reaction with production of other just energy or alpha particle, proton, neutron, or alpha proton is disrupted actually. And here in neon burning can be seen before at the lower temperature, but is a little less than 1 billion. Using alpha particle produced by here, because when there is a neon burning, all the helium is already depleted, so you cannot have helium. But you have here some reaction that can produce them. Oxygen burning. Oxygen, a really stable nucleus, so is not easy fusion. So you need 1.5 billion Kelvin to produce it. And you have few years before the core collapse at this point. You have this production, then you see that energy for immunity is always small. The silicium burning can produce iron, nickel, and so on. Can lead also the silicium burning, also silicium photo disintegration. That essentially more than you can burn in this way, or you can disrupt one silicium in alpha, and then alpha enter and arrive here in this cycle. Classical, this reaction of nickel is what is produce a lot of energy, and it is what maintain the luminosity of supernova. This reaction, nuclear reaction, the result of the silicium burning, it is stable, absorb an electron, and you have a lot of electron, and you can produce this one at the end, having the iron that we will see. In definitely higher, at 7 billion Kelvin, you can have the photodissociation of the iron in 13 alpha particle and 4 neutrons. or also the disruption of the helium particles, so you can produce proton again. The slow and the process, you have two reactions, mainly the neutron capture. Nucleus can capture a neutron and goes in an atomic number higher, or one neutron can decay and maintain the atomic number by increase the mass number and increase the atomic number with the beta decays. As if the nuclear capture is faster than beta decay, you have a rapid process. In the other case, you have lost process, and these are producing most of the particle above the iron. That is also what was observed during the merge of neutron stars, where there are a lot of neutrons available. There is also the pair production. Essentially, a photon is converted in a pair during interaction with the ion. It has a similar effect as ionization. Neutrino production. You have photoneutrinos, pair neutrinos, plasma neutrinos, and Breslau neutrinos. You can see here the several behavior, and usually you need really high density or very high temperature of the order of billion Kelvin. No billion. And at the end, you see the main productions here. You can calculate the production rate is 20 erg. That is quite low. And men produce a lot more energy by grams by second, but the star is definitely bigger. And if you do the calculation, you see that as we see at the beginning with 20, you saw 2, so the fraction of the mass is more or less 1/10. So the mass core, you see, after seeing all the corrections, because you have to correct also for the fraction mass of the hydrogen, because you're not using all the core, but just the 70% in the sun. Then mass core is like the 14% of the core, with the radius that is more or less 30–40% of the radius of the star, at least in the sun. Gravitational energy can be little production. We saw the contraction is just keeping according to several values. Can be the star can have can contract, produce energy, or the other. Time scale, typical free fall is this time radius divided by the acceleration gravity, the expansion in R by divided the gradient of pressure divided by the density divided by T, divided by the square root of pressure divided by the density is isothermal sum speed. So the velocity of the pressure wave. And the static is that when the two are more or less equal, is the time when the system can react in a static equilibrium. The contraction with the Kelvin-Helmholtz, the time that stars can produce is a luminosity just by contraction, is this value, and you see that is around 10 million of years, more or less, for the, something like the sun, in which the nuclear time scale for hydrogen is the order of the 10 billion years. The anni, because annus is actually should be the unit of time, considering the years. Then we saw the star structure that we use all the boundary condition. We see again simple stellar model, the von Russell theorem that is permit us to say that essentially given mass distribution of chemical element will determine all the characteristics of the stars. The evolution tracks that are very several properties during the time can be determined. To make a way to make a solution matching, we split in several parts and match in each point to have the matching point. All the properties must be continuous and the derivative must be continuous. And then polytropes, but I think we stop here because technically going 1 hour more than should be. Thank you for following. I hope the sharing part is okay. See you.